Hi, welcome to Science Central. I'm Mr. Gary, and today we are going to talk about simple machines. So let's first define what a simple machine is. So, a simple machine is a basic mechanical device that can change the amount and or direction of force one must exert to move a load. So what is a load? Well, for today's experiment, a load is going to be this, a 500-gram mass. So a load, definition is the object or mass that is being moved. And how do we move an object or a mass? With force. And what is force, you ask? Well, force is any push or pull on an object. So if I push the object this way or pull the object this way, I'm applying force. That also applies if I'm lifting the object up or placing the object back down. So if you take force and the distance that it moves, we get work. So work is defined as work done to move an object is defined as the force required to move the object multiplied by the distance of that object travels. So W equals F times D, or force times distance. So let's start out with a simple idea of work. We all kind of know what that is and how that looks. But let's take a look at work on this mass or load. So if I had to do a job that required me to take this mass or load from the ground and place it up here on the ledge all day, this is what it would look like. Oh gosh. Okay, I better stop there. Now, there's got to be a better way to do that because, one, I'm getting old, and you could tell I was getting winded back there, but what other problems do you think I might have? You know, maybe a pulled arm muscle, maybe a strained back, maybe a twist that just didn't work quite well. That's a lot of physical work and possible physical damage to me. There's got to be a simple machine that can help me do that work. And that's one of the reasons why we study simple machines. Now, today we're going to look at 4 different simple machines. We're going to look at pulley, an inclined plane, a wheel and axle, and some levers. So, to make this comparison of all of these simple machines on whether or not they helped us do work or improved our work, we're going to have to be able to compare the force we use on each simple machine or setup. So, to be able to do that, we need to set some parameters in our experiments today. And these parameters we're going to set as constants. The more constants we can set as we look at each of the individual machines today, the more we can just compare our force. Before we do that, we're going to set our constants and we're going to take a look at that definition of work, force times distance. So the first constant we're going to set is our load or our mass. So our mass is going to be this. It's a 500-gram mass unit. So the way that we are going to measure our force is with a spring scale. So this is a pretty interesting scientific object. We have a spring up here, a plunger with our markings down here to measure our force or our mass, and a hook down here at the end. Now, the way this works is we hook our mass or weight at the end of our spring scale. We lift up, and you can see our spring starts to stretch. Our plunger moves on our scale, and it tells us exactly how much our mass we have here. Now, there's two sides to this scale. One is in grams, and our gram reading right at the moment is 500 grams, because this is a standard 500 gram mass. And our back side is in units of newtons. Now, newtons is a unit, just like an inch or a centimeter or a gallon. It's a way that we describe or label a force. So newtons. Hey, do you know what Newtons were named after? Or the scientist? Sir Isaac Newton. That's right. The guy that got that apple dropped on his head. So we're going to measure our newtons today, our force in newtons, and this is a 5 Newton mass. So it takes about 5 newtons of force to raise this mass off the ground. Now, how far we raise it off the ground, remember that distance that we needed to work with? Well, we're going to keep that constant today too. And we are going to move our mass or our load a distance of 15 centimeters. Now, this is inches. 15 centimeters is approximately 6 inches if you're using the American units. Now, in science, always remember we like to use the international system, which is centimeters and grams, because scientists like to have one common language to use, and that's the international system. So, let's take a quick look and do that math that we were talking about. I know, math can be kind of tricky, but the good news is I kind of filled in the blanks for you. So let's take a look at that. All right. So, here is our basic work. Work equals force times distance. So our basic constants that we're going to use today is force. Lifting our mass here without a simple machine requires 5 newtons right there. Our distance that we moved, (15 centimeters). Force still is the same at 5. So what we like to do is plug and chug. Plug our 5 in here for our force, our 15 centimeters for our distance. We multiply those together and we get 75 joules of work. So the joule down here is the unit that we describe work. Now, we could do this calculation for every single one of our simple machines today, but we're going to take a shortcut because we don't have a lot of time. And I also don't have a cool worksheet for you guys to fill your numbers in on. So we're going to kind of compare just our newtons. Since we're keeping our initial force constant and our distance constant, when we compare the force we use, we're going to be able to kind of directly judge or kind of estimate how much work would be done. All right? That might make a little more sense once we jump into our first simple machine, which is going to be our pulleys. So, just a quick reminder. So our force is 5 newtons, our distance is 15. That's our constant. So all we have to do is compare our force. And let's get started with our pulleys. All right. So here are our pulleys behind me. We have a single pulley, obviously, just one. And we have our double pulley, which is obviously, again, 2. So let's start with our load. Down here on the table, we are going to
hook that right there. And here, let's flip this around so I can actually read my newtons. Here's our distance. We're going to lift our load to the top of our distance, which is 15 centimeters, and I am looking at a Newton force of 5 newtons. We'll put that down. All right. So, our single pulley right here is 5 newtons. All right. So let's see what our double pulley pulls us. So we move our load, set up our distance, grab our spring scale, and pull right there. Will you look at that? The force is 4 newtons. All right. So let's see what we got. 5 newtons for our single pulley and 4 newtons for our double pulley. So, did our double pulley make our lives simpler? Did that simple machine work? Well, by the definition of if we use less force to raise that constant mass, then yeah, it did. Our double pulley required less work because it required less force. That's pretty cool, huh? So let's take a look at our other machines. Next one on our list is the lever. All right, so let's move some of this stuff out of our way. Let's set up our next experiment. Oh, it's going to be a problem. Hold on. Technical difficulties in the science room. Got to get my load off of there. All right. All right. Let's set up our lever. So this is going to be our fulcrum, or our pivot point, for our lever. Yeah. Move my arm so you can see the whole thing. So the fulcrum is basically our pivot. So if you've ever heard of a fulcrum in a lever, that's going to be the point where the action kind of works. So let's start out with A. We've got 3 different fulcrum points, I should say, on our lever. We have an A, we have a B, and we have a C. So I can do that. All right. I am kind of blocking the view here, so. So we have our distance marker. We have our mass. We have our spring scale. So let's start out with A. Let's attach our mass to one end. Our spring scale. Make sure I have newtons pointing towards me. Let's see if I can do this. My arms are long enough. We're going to see how much force it takes to lift our load up 15 centimeters up to there. And we are at 6 newtons. So, if I can get my assistant Justin, Mac, to hand me my lever paper, we are at 6 newtons. Alrighty. So let's go for B. Keep everything constant, and we'll move down here to B. This one looks a little more tricky. So get our distance. Let's get my top going. Oh, technical difficulties again. There we go. A little bit better. Actually, Matt, can I get your help again?
Mm-hmm.
Can I get you to put your hand right here at the fulcrum just to make sure it doesn't slide off?
Yep.
Thank you. All right, and our distance, and we're gonna pull. That's weird. Huh. I didn't take hardly any force at all. Got about a 0 on my spring scale. That's a little interesting. All right, let's see. Let's mark that down. I'll move this back to A so I'm at a neutral point. All right, so fulcrum B equals about a 0 on our force or our newtons. So let's see what C brings us. All right, I think I'm going to have to move this down just a tad bit. Slide that down to C. All right, this one's going to be a little bit better. And we're going to hook that onto the end. All right, we got a little bit of force going. And pull. Keep pulling. There we go. Oh, my word. That's a lot of force. Let's get that about there. And, oh, my word, we are off my spring scale. So my spring scale goes up to 20 newtons. We are over 20 newtons. Probably somewhere about 30 or 40 almost, according to my estimate. So I'm going to write on our board here. Put it out here. Actually, pull it back here so I can read it. Equals 20. I'm going to put a big plus sign over here. Newtons. So, let's take a look at this simple machine. This one's kind of interesting because it doesn't work necessarily like those others. So, our position A, which is kind of in the middle here, distributes our distance from where our load is down here. And since it's equal distance on either side of position A, notice that 6 newtons was very close to a neutral of 5 newtons that we used to begin with. Now when we move that fulcrum down here and we shorten this distance, that was really easy to move. So we have a shorter distance, but a longer distance over here. So we have more. Obviously, this kind of goes in with the word of the simple machine. We have more leverage down here to move that mass. And then the opposite happens when we move to fulcrum C. We have a short amount of leverage here and a longer distance over here, so it requires a little bit more force, or a lot more force, according to our chart, on how that simple machine worked. But as you can see, those different positions and that distance of our fulcrum here did require a lot of different forces. So, which lever or fulcrum point worked the best? A, B, or C? Obviously, B. So, and our next simple machine on our daily experiment is a cart. All right, so let's look at the wonderful invention of the wheel and axle. So,
Who doesn't love a good car ride? I, for one, love a good ride around town, especially in this time of social distancing, where we can kind of still get out and still be safe. So let's take a look at a cart without wheels and a cart with wheels. So we are going to use our distance again. We're going to set that right there. Our mass is going to be in our cart without wheels, and I am going to pull on our spring scale. See what our force is. So as we move our cart, and we have to overcome the friction of the table here, we are getting a reading on our spring scale of about 1.5 newtons. So if you have noticed that a couple of times during our experiments, we've changed the color of our spring scales. Those spring scales are a little more sensitive depending on its color because of how tightly wound that spring is. It gives us a better idea of the newtons. So this one was a 1.5 newtons. So let me grab our chart here. So no wheels, we have 1.5 newtons. Now let's see what that wonderful invention of the wheel and axle does. So move that out there. We'll move our measuring stick there and start to pull. That's almost like that other fulcrum. All right, I think I better switch this over so I can read my newtons just a little bit better. Let's run that experiment one more time because I had a little bit of trouble seeing exactly what my newtons were, and there we go. All right, so my newtons on this one was 0.5. Now, when I do decimals and it's below 1, you always like to put a 0 in front of there for that placeholder. So our 0.5 newtons. Now, so what do you think about this simple machine? No wheels, a lot of friction to overcome as you're pulling that open cart with no wheels. But yet, when you add a wheel and axle to that, the cart moves rather smoothly. So again, since our weight is constant and our distance is constant, we can kind of see and compare just our force that obviously that wheel and axle makes our lives a lot simpler. So, and then our last comparison that we're going to look at today is the inclined plane. Short board versus the long board. Let's see what we get. All right. One moment as we move our experiment. So we have our long inclined plane and our short inclined plane. Now, on both of our inclined planes, you can kind of see that we already have our marker up here. Again, it's a constant 15 centimeters, about 6 inches. And we are going to look at how much force it takes us to raise our mass from the bottom of our board to the top of that mark. So we're going to grab ourselves a spring scale and pull away. All right. That was about 5 newtons. We're going to run it one more time just to make sure that I got the right reading. Because in science, we do like to repeat our experiments just to make sure we are accurate in our readings.
I'm going to run that one more time. I actually got a different number than the first time. I got about a 3. This one's a little tricky because you kind of have to apply a constant force to get it to move. Off that initial platform edge. One more time just to be on the safe side. And, all right, I feel a lot more confident in that number since I ran it 3 times. That was about 3.5 newtons. So we're going to put that on our short board. 3.5 newtons. Now let's see what our long board gives us. Again, science is always fun because you can never tell when you're going to have technical difficulties. There we go. All right, here we go. And just to keep things constant, I'm going to run this one also 3 times. To get a good idea of our units. All right. So that was running about 1.5 newtons. So, which simple machine worked better? Our short board or our long board? Again, 1.5 is a lot less than 3.5. So our long board spread that distance out, which spread that force out, which made our work a lot easier. So, as you can see, simple machines come in many different shapes, sizes, and forms. So my challenge for you today is working with things that you have around your house, such as Legos, some simple craft supplies. Find a way to build a simple machine. Have fun. See what you can find, and see if you can make some challenges to see whether or not different types of simple machines that you make can make your life easier, or the force that you use to lift an object easier, as we did in our experiments today. So I hope you learned something and had fun today. We have a tradition here at Science Central. If you did those things, we would like you to yell with me at the top of your lungs, "Science is fun." I'm going to give you a count of 3, and we're going to yell on 3. Ready? 1, 2, 3. Science is fun!